So today we're happy to have Bezrukavnikov from MIT and IAS. The title of his talk is Affine Hecke category and non-commutative Springer resolution.
Okay, thanks. Yeah, thanks for the opportunity to revisit this material. So, in the previous talks, I mean, I will not really use that much from the previous talks, but it was explained in the previous talks that there is an equivalence between two geometric realizations of the Affine Hecke algebra, so the constructible side and the coherent side. So we'll recall the exact statement in a few minutes. But today I want to talk about additional properties and applications. And the main focus will be on comparing the abelian category, more precisely kind of locating the abelian category of perverse sheaves on the fine flag variety within the coherent category, or in other words, describing the T structure. So, well, the goal in doing so, there are maybe several applications, but a major motivating application was to model representations and Lustig conjectures, so what was known as Lustig's hope, as opposed to Lustig's conjectures about irreducible characters of algebraic groups. So this is about irreducible representations of modular Lie algebra. But sort of before going into that, there will be a quick section about kind of general feature of this equivalences, which addresses the following point. So, well, as I say here, so we discussed these equivalences, and we said in the beginning, so that our motivation is the an isomorphism between two realizations of the Affine Hecke algebra, and we're trying to categorify it. But if we actually go back and see what we have achieved something weaker, because if you take the K group of both sides here, you'll only recover the affine Y group, right? And so if you want to actually recover the Affine Hecke algebra, so that would be the K group of G check times C star, or if you're working over an orbital field, you should say GM. Sorry, GM of the same thing. And introducing this GM is a sort of tricky business. So one can talk about upgrading the equivalence to a version where you have GM in the right-hand side, and then you have to say what you have in the left-hand side. This will be some discussion of mixed sheaves, and this is possible but involved. But there is a sort of more concrete, perhaps, I mean, a formulation which requires less work than I'm going to present now. And another kind of reason why we want it, it's not just, which is, more serious, okay, a more serious one is actually addressing these applications that I already mentioned. Basically, eventually we want to apply the theory of weights, right? Modeling the old proof of Lustig conjectures, so which I recall here in a few words, right? So in the proof of Lustig conjectures, so there is some road one needs to travel, so one starts with category or finds geometric realization, but then eventually one applies a big theorem which says that Frobenius, also here, Frobenius acts on certain x1s between weight zero sheaves with positive weights. And that can be translated into a statement about grading in category or that one wants and that one knows to imply causality conjectures. So we do need to bring this Frobenius weights into the picture, and we do need to kind of say something about them on the coherent side. And so a direct way to do this that I like is the following theorem. So we put our, well, I didn't say what K is, but so K is FP bar, where we work with affine flag variety. So the dual group, so the are defined over the field K. And if K is FP bar, then we can talk about wave sheaves and action of Frobenius. So that will be just an auto equivalence of our category, which will not do anything to reducible objects, but it will act in some non-trivial way in the category. And I just say that that particular equivalence can be identified on the dual side with dilation by Q. So it's just, so there's this nilpotent here, X. And I send this X to QX. So Q is just, yeah, it's Frobenius Q. So, yeah, so all the equivalents we discussed, they have this property, and I don't say here anything about the proof, but this is kind of clear from the first principles. So this basically follows, so maybe I should say something now. So this follows from the construction, because the meaning, as was discussed in the previous talk, so this guy X comes from log monodromy acting on the nearby cycles or nearby cycles entering in the definition of Gaisgeri's central sheaves. So basically, since we have this relation, since Frobenius M is equal to M to the Q Frobenius, this is just a relation in the Galois group of FQ of T. So it formally implies the theorem. Yeah, I'm not giving you a complete proof, but this is just trying to communicate the feeling that this is something very natural and just essentially built in the construction. And then we can just use it without really, saying what geometric category corresponds to GM covariance shifts. Or in fact, we can just use that and we can postulate mixed shifts to be the GM covariance shifts on the coherent side, and this can be used to compare that strange definition to something geometric involving wave shifts. But in particular, we know that if we start with two, so if F is in actually in the category of G check times GM covariance shifts on, say, this time variety. So then its image in di of flex, the category that was considered in the previous talks, has a wave structure, because wave structure means that you can Frobenius equivariant, but if it's C-star equivariant, it's particular equivariant for dilations with respect to any element in the multiplicative group. So requires wave structure. And for FG in this category of G check times GM equivariant sheaves, if I consider X between the images, so I forget now what was the let's say this is phi. So if I put this D, so GM degree G part, sorry, here I maybe should say just X from F to G, the part in degree D. Will be isomorphic to X between phi of F and phi of G, where phi is the notation for the main equivalence. And so here I'll have Frobenius way D. Oh, yes, sorry, it's not, it's okay, so that's the end of this section of the talk. So maybe I should pause for questions. It's a very general remark on a way to bring weight here.
Sorry, I missed it. What's a wave structure?
So the point is that suppose I have a GM equivariant sheaf, right? And in particular, it's equivariant with respect to dilation by Q. And so then it means that by this theorem, its image under the equivalence is going to be equivariant under Frobenius. So this is the way. I mean, I may let's say its image in the constructible side is perverse, so as to avoid unnecessary homological algebra complications. Okay, did I answer the question? Oh, okay. So yeah, I mean, let's say assume that by wave structure I mean just isomorphism between F and the image of F under Frobenius, F under Frobenius, and it is actually this is indeed only fully justified if the object is, say, perverse. But that's what we need for the application. Okay. All right. So with that, I can get to my kind of main part. And the main part is, as I say here, is about the question that I already described verbally, so about describing the image of perverse sheaf under this equivalence. And, you know, I just tried one of the equivalences, but yes, so let's, yeah, again, all or most of the talk will be answering this question, but there will be some discussion kind of to prepare for the answer. But so first I want to present actually the following concrete statement that in fact, in terms of how the things are proved and the theory is built, it's proved in the end, but I think it can be helpful to see it first. Okay, so here, yeah, I discussed the relation of perverse sheaves on affine flex to important orbits. And for this, I need to recall the notion of intimately familiar to many of you, that of a two-sided cell in a Lustig's two-sided cell in a Weyl group, perhaps a fine Weyl group. And so just, I will just say basic things about them. So these are certain subsets in the corresponding Weyl group, partitioning the group. So it just broke into this disjoint union. And the set is partially ordered. And the key property is that if I collect all elements in one cell and everything which is below it, take the corresponding elements in the Lustig basis, and then the span is going to be two-sided ideal in the Affine Hecke algebra. And that's essentially the finest partition with these properties, the one we want. So it's essentially a characterization. Okay. Yeah, so I'm sure many of you know much more about it than I do. And there's an obvious categorification. You can just take your Hecke affine, the corresponding Hecke category, affine or affine, and just which I denote here by H, and you can consider the full triangulate subcategory generated by the corresponding IC sheaves, whose marks in W lie given cell or lower one. So this is going to be a full triangulated subcategory, and I didn't write it, but it's clear from how these things work is that this is a monoidal two-sided ideal. So from this point on, we focus, so this was a very general discussion, so now we focus on our case when W is the extended affine Weyl group. So then Lustig, in his papers on cells and affine Weyl groups, he constructed a bijection between two-sided cells in the affine Weyl group and important orbits in the dual Lie algebra, which I here denote by cell C going to the orbit OC. And I want to say how this bijection really it fits into our picture. And the answer is very nice, and perhaps, you know, guess at this point what it is, especially once you see this notation. So the notation is that, yeah, so I take, so there is a standard guy, and the standard guy maps to the important cone. So I can take the pre-image of a given orbit and call it something. So it's pre-image of OC. Pre-image of OC is the standard C. And I can close it. And I mean, since the map is proper, it doesn't matter. I can close in, take the closure in the nil column and take that pre-image of that, or I can take pre-image and close. About one of the things here, but both give the same result. Okay, and now I have this proposition that the equivalence advertised earlier sends the monoidal category, you know, the cell canonical category into this geometric thing. So the filtration by cells corresponds to filtration by orbits.
Roman, do I understand correctly that they're not the same and you still need to take the preimage of the closure of O instead?
Yeah, but there is preimage of the closure. So
No,
less
but Steinberg is Lagrangian, right? I'm a little bit confused. So Steinberg is Lagrangian, so all components have the same dimension.
Yeah.
And the preimage of O will be some of these components.
Yes, but so what? I think it works as. Oh, good point. So yeah, thank you. Actually, excellent point. Sorry, I was thinking about something else. So really, I said that two things give the same result, and they don't give the same result, and only one of them works, and actually it's not the one I read. So okay, so let's correct it. Thank you. Be the okay, so we'll do it this way. So we'll insert one more here. Of the closure of yeah, because I was kind of yeah, there are always settings, and in the Whittaker setting where you work with until then both formulations would work, but here only one. Thank you, Annie. But okay, now I think it's okay.
Yep.
Any other questions or comments? Yeah, okay, so I said it in words, but yeah, so in notation I use this support condition. So yeah, that's as a lower index here, and this is means that yeah, C of x is coherent shift on x, set theoretically supported on Z, which is the same as they vanish on the open complement. Okay. All right, so yeah, I don't say anything about the proof. As I said, it's actually follows kind of in the end when everything else is proved, and we can, yeah, if someone is interested, we can discuss a little bit in Q&A or elsewhere. But the reason I want to show it first is because it's already illustrates that somehow the constructible side is nicely compatible with the geometry of important orbits. So, and yeah, by the way, this also, I'll say a little bit later, that, a little bit about that later, that this allows to analyze the asymptotic Hecke category in coherent terms. But okay, so for now, yes, for now, let's just be happy that constructible side really knows about important orbits. And okay, so here I start with a informal comment that this coherent description of perverse sheaves on flags, it has kind of two aspects: global over n and local over a given orbit. And I start with talking about the global one, global over, again, important column. And this involves this curious ingredient, which is mentioned here, just perverse coherent sheaves. I mean, I should say equivariant because otherwise it doesn't make sense. As you will see in a few minutes. Okay, so now, so I focus here on the this particular equivalence, although it's all applies to other ones. But let's focus on this one first. So this is the Whittaker one, which was maybe explained by Saucian. So when in the right-hand side and the coherent side, we just have equivariant coherent sheaves on the Springer resolution. And so then I want to further manipulate it to make things even simpler. And I want to make the right-hand side just to, I want the flag to disappear and just work with the nil cone. And it's essentially the same procedure that reduces us from the full Iwahara equivariant sheaves on the flex to this Iwahara-Whittaker sheaves on flex. So it's kind of, on the decategorified level, it corresponds to taking the image of the anti-spherical projector, by which I mean the sign idempotent in the finite Hecke algebra. But here I phrase it a little bit different way. So in this combinatorial way. So as you see here. Okay, so let's recall that irreducible objects in the corresponding perverse sheaves category on the constructible side are indexed. So in the full category indexed by the affine Weyl group, and then we have exact functor of Iwahara-Whittaker averaging, and that functor kills quite a few objects, and the ones which survive are the ones which lie low and don't stick their heads out. So the ones which have minimal length in the corresponding coset of the finite Weyl group. So W here is the finite Weyl group as opposed to the fine one. Okay, so this is the indexing set for irreducible objects here. And now in this set, so this set is in bijection with co-weights G. Let's say consider a smaller set, which is in bijection with dominant co-weights. So it's in bijection, namely the minimal length representatives of two-sided cosets. So these are okay. And now I'll just artificially kill those ones which stick their heads to the right, which are not minimal in the right coset. So I just take the quotient instead of. It is okay. So as I okay, and I take this. In fact, I could have mentioned here that this D Iwahara-Whittaker happens to be equivalent to the derived category of the corresponding perverse part. So after I take the quotient, I still get the derived category of the part. So okay, so it's nice a little category. And yeah, as I said, this is a categorification of the taking the image of the sign idempotent, both on the left and on the right. Okay, so now here's a theorem that which actually appeared some years before the full equivalence of categorifications of H affine. So this category happens to be equivalent to sheaves on the nilpotent cone. But okay, so this is maybe just another one in the list of the equivalences that we already discussed, and maybe not more impressive than this. But the point the reason I want to state this particular thing is because in this version, there is a very neat answer to the question about structures. And here is this neat answer that under this equivalence, the abelian heart here, goes to the so-called perverse coherent sheaves of middle perversity on the nilpotent cone. And this is actually, yeah, the maybe only statement that I'm going to prove. So let me first explain what it means. Yeah, so first just one word about A. I already said something to that effect verbally, that, yeah, its antispherical thing to the Whittaker is like the Whittaker of the flags to DII. So kind of SAT style description of the situation, but yeah, so it's I'm just saying that, you know, if you believed all the previous currents, you should also believe this one. Will not spend time to prove it. It's actually not hard to explain. I actually considered including this, but we'll just take time, a little bit of time. Essentially, it's an exercise on the previous lectures to show, for example, that the kernel of this antispherical projector is also the kernel of the push-forward functor from n tilde n. Yeah, maybe just to clarify this a little bit, I should say that there is a commutative diagram, right? So there's the Whittaker of flags is a dB core. And then this goes just by the projection. And here, well, if I was Vanya, I would have asked someone from the audience to say what it is. But I'm not, so I'll give you the answer. So it's yeah, it's the just the direct image function, where pi is of course the projection from the Springer map. Okay, so yeah, but so first, well, so yeah, I want to explain a little bit about the proof of B assuming A, but before saying what the proof is, I just need to say what the meaning of a statement is. Yeah, so it turns out that there is actually was something I found out when I was postdoc here at the end of my stay here. Well, it turns out, and maybe it's not very surprising, although I, wasn't taught it when I was taught about perverse sheaves, that the perversity structure can be defined on the derived category of coherent sheaves, which the theory works somewhat in parallel to the constructible theory, but there are several differences. Namely, well, so I want to state it for a stack, but the only stack we'll be interested in is n mod g. So I could also talk about equivariant sheaves. And the so we need to be given a perversity function, which is just a function on all points of the stack. So in our case, points just corresponds to orbits. And it has to be monotone and comonotone. If you want to, if you want to build a theory for constructible sheaves, there are actually no restrictions. You can, the most commonly used, the most useful perversity is the dimension perversity, with P of the stratum, or you could say Zariski point is a minus dimension. But you can also take any other z-valued function. But here, if you wanted to preserve so if you want it to be defined on derived category of coherent sheaves, you need it to be monotone and comonotone. Like maybe without writing it down, like I want to say that, say if you For example, you know, like a typical thing to do is to when you construct when you work with perverse sheaves is like Stalin's construction when you extend, say, by star and truncate. But just the point is that if you extend a coherent sheaf by star, you typically get a quasi-coherent sheaf. But you can put yourself in some situation where you're under some conditions, if you do that, you know, if you truncate in a degree kind of which is low enough, then you still get something coherent. So this motivates the answer, which is also can be proven. So the function, the perversity function has to be monotone and comonotone. So basically, when you go down in the junction order, the perversity function has to go up. So that's the first condition, but it can't go up by too much. So in other words, the this is equivalent to saying that the dual perversity function. So yeah, I see Ben's question. I'll say in a second. So it's a dual perversity p prime of x, which is minus dimension of x minus p, is also monotone. Yeah, so that's another thing that in the constructible setting, you can just easily restrict to fixed certification. But in coherent setting, at least naively, this is not possible because you know, you can require that a complex is a vector bundle on a the sheaf or complex is locally constant on a given stratum, but such sheaves do not form a full triangulated subcategory. You can always consider like R goes to O by F, and if you know, if you're in the local systems world, then the rank is locally constant. But if you're in the coherent world, then it is not, and there will be some kernel that will be have singularities on other strata. So so it's not. Yeah, there's the modulus of x is not this. There's no way to meaningfully restrict to a set of strata, so you just have to work with all, say for the scheme, with all the risky points, and for a stack also with all points. Right? So perversity has to be defined. Only the limit over all stratifications can be worked with, so to say.
Sorry, though, can I ask then, is your notation for P, like what is the domain then, the set of K points or something?
For a scheme, yes, and
okay.
yes. Set of points, and again, for us, the only example that we care about today is that the set of orbits. So that
I see, thank you.
Okay, but so so that's fine. But in fact, well, then, you know, much, you know, of the theory of perverse sheaves is about studying IC shapes, right? Well, there's first classification of reducible objects, and then one can, you know, say a lot about those. But it turns out that this sort of construction of minimal extension and corresponding classification of reducible objects is actually works in this setting, but under a more restrictive assumption, namely, you need to as I say here, just the inequalities have to be strict instead of less or equal. I mean, it has to be, the perversity function has to be strictly monotone and strictly comonotone. And it's all good and nice, but then you discover that, you know, if you just take a scheme of positive dimension, there is no such things, because, you know, there's always is a risky point of codimension 1 in every pole. if you have a Zariski point of some positive dimension, there will be a Zariski point in the closure in codimension 1. And then you cannot, like, it has to be an integer value, and there's no room. I mean, it has to drop, strictly drop, but strictly less than 1, and then that's unfortunately impossible. But sometimes it does work. Namely, if you happen to be working with a stack which has a discrete set of points, so say group acting with finitely many orbits, and all orbits, for example, have dimension of the same parity, or more generally, yeah. What you need is that there are no junctions of codimension 1, but yeah, parity is a good way to ensure it. And of course, in the nilpotent cone, all orbits are even dimensional. Then you can define this nice middle perversity, and the whole story works. And yeah, so that's what it is. But actually, I should have put. I think focusing on this example was my idea, but in fact, I think they were discovered that it turned out that this was also discovered by Deline, unpublished, and then there were papers by independently. There were papers by Gaber and Kashiwara. I think they were all pairwise independent. And then kind of we wrote it also with I think.
Roman,
Yeah.
is it okay if we take a short break before we go on to application of this concept to
Yeah, excellent.
yeah. So we'll meet back in 5 minutes or so, but in the meantime, we can ask questions.
So I can have like about 30 minutes after the break. Is that good?
Yeah, I think we can
20.
Yeah.
50. Okay.
We will see. I think you are at about halfway, right?
Yeah.
This. Yeah.
At least halfway, maybe. Okay. Yeah, there was actually a letter. I mean, I talked about it to Deline back then, and he wrote to me a letter, which unfortunately I lost.
Roman, can I ask an example? If you take like stack of local systems on an elliptic curve, I guess it's zero-dimensional stack with some sort of duality, like symplectic structure. Does that thing have like a perverse coherent and well-behaved perverse coherent T structure?
I can mention an example that's yes, that's close. Maybe it's even. So sorry. So do you know that in this example that the orbits are even dimensional?
I don't know. I was just going off the zero-dimensional thing.
Example in which we can say maybe here. So another example. That I know about, it's a affine Grassmannian. So it's a affine Grassmannian modular the GO4 action. And then it's known that on every component, orbits have dimension of the same parity. And so in this case, the theory works. And so we just made this observation and posed the question in a paper with Misha and Ivan Mirkovich. So And then it was followed up by some people. So at least in type, so one can ask, we in particular compute the K group, and this gives a basis in the K group, and one can ask what's this basis. And it was related to cluster algebras, but I will not be able to say more. And I'm trying to remember the name of the author.
Cottis and Williams.
Huh?
Cottis and Williams.
Yes, that's right. Harold Williams. And maybe the paper is trying someone. Maybe Cottis. Yeah. Okay. So I don't remember the exact status. Maybe they answer the question in type A, but not in general. There was also some other paper by Finkelberg's postdoc, but I can I'll provide a reference later. Yeah, I think Misha is not on the author, but it's just. But yeah, as far as I know, the question for other types is still open and can be very interesting to investigate. Okay, just let me know when I can restart.
Yeah, if people have no other questions, I think we can start.
And okay, yeah, so well, I'll have it on the slides on the next slide, but another idea which is many people proposed in particular is that another source of sheaves which would be smooth on stratification, coherent sheaves would be smooth on stratification with different dimensional strata would be some sort of hypercomplex or hyperkähler geometry, but I don't know if that has been followed up. I think it has not. But okay, I'll mention yet another example. Next slide. Okay, so so now I promised you one proof, and the proof is actually very short. So it turns out that just using that the Springer map is semi-small, one can convince oneself just pretty much as one does in the constructible setting that if you take a direct image of a line bundle, it will be from under the Springer resolution, it will be perverse coherent. And then with a little bit more work, you can check that in fact it characterizes the T structure. You have a bounded T structure whose heart contains all these guys, and then it has to be that. It has to be perverse coherent T structure. In fact, it's enough only to look at dominant and anti-dominant ones, because it's something like a highest weight category where direct images of dominant weights, like semi-ample line bundles, form co-standard, play the role of co-standard objects, and the ones direct images of anti-dominant play the role of standard objects, so have a separate paper about it, but yeah, so there's this way to think about it. So maybe I'll say this here enough to consider L to be of lambda, where plus minus lambda is dominant. So these play the role of core standard objects or standard. Where in this P-core category, which is something like a highest grade category. And yes, I must confess that this paper is written completely in the context of geometry of important cone, but the guiding ideas came from this equivalent. It has not been written at the time, but the picture was there. Okay, so right, but then so it remains to check that direct images of line bundles correspond to something perverse on the constructible side, but that is already here, right? Because I drew this commutative diagram for you, and then we know that. So if you still remember like basic features of the equivalence from the previous talks, then there's line bundles on diagonal or of lambda in the Whittaker thing. It just came from this Wakimoto sheaves, which were perverse. And then in fact, I'm only mentioning these Wakimoto sheaves for to make the transition between sentences smoother, but really we only need to consider this case when it's either dominant or anti-dominant. We only need to consider this, but then they are either standard or post-standard, so you don't even need to think about Wakimoto sheaves. Okay, so this is a quick and easy proof. But the fact is surprising, and I mean, I'm still feel that there may be some room for generalization, and there should be some context within, say, geometric lengths and understanding how T-structures interact with it, where this Pythagorean coherence should play a role. But in particular, so I just want to mention this thing which sounds similar but has not really been connected, and I'm hoping it will be done at some point. So this is a paper of Chris Schnell that I really like, which there's this geometric Langlands for GIL1, which is, I think it's known as Polishuk, Rothstein, and Lamont. It's some equivalence of categories like D modules on billion varieties and coherence sheaves on local systems. I will not write things down, but the point is that so the problem that Chris Schnell addresses is what. So there's some equivalence that these people wrote, which. But what if one just takes an actual holonomic D module and takes its image? What do you get? And the answer is that you get, again, a perverse coherent sheaf of middle perversity with respect to certain stratification, so to say. But so again, there was also Langlands, and there are also perverse coherent sheaves. But yeah. Okay, so this is just to mention that thing that I hope is related. Okay, so now I think I said what I meant to say about the, so to say, global aspect. So that's global again over the nilpotent cone. And now I want to sit on a given orbit and say something about what's happening there on the essentially on the Springer fiber or square of the Springer fiber or something like this. And that is really where this non-commutative Springer thing comes in. But to talk about, to motivate, so non-commutative Springer is some non-commutative resolution of the nilpotent cone, which will be characterized in terms of the thing that I want to describe now, in terms of the action of the affine break group. So notice that this constructible, the monoidal constructible categories that we were discussed in this series of talks, they actually come with sort of embedding of the affine break group. It's just I mean, after all, they categorify H affine, and H affine is one of the definitions is that it's a certain quotient of group ring of the affine break group by some quadratic relations. Now forget about the quadratic relations and then just remember the affine break group. But okay, so this is a vague motivation, but it's very easy to actually construct such a homomorphism. I mean, here I mean weak homomorphism. I mean, we heard a talk by James Tao who explained that construct. Affine homomorphism is a tricky business, although apparently it's also now can be done due to the K by 1 conjecture. But here I'm only interested in the weak homomorphism. So homomorphism to the group of isomorphism classes of invertible objects in my monoidal category. Yes. So as also James emphasized, one can give this presentation where it's generators are in conjunction with the affine wild group. In fact, everything can be also extended if you like. And so if I send the canonical representative into, well, I preferred co-standard objects, and maybe I shouldn't have said it shouldn't be called TW, but never mind. This notation is not never used again. And then the standard properties of convolution ensure that we get homomorphism. And now, so translating it by via the equivalence, we get a homomorphism like this. But the point here is that the first point is that you can write a very neat formula for how the generators act, and that's the content of this theorem. Well, I mean, maybe, well, the content of this theorem is maybe not really, this theorem is really tautological consequence of the previous thing and the equivalence, but the point is in the next few lines that we have this explicit description. And the explicit description is given in this so-called loop presentation, or Bernstein presentation of the affine break group. So it's generated, it has, well, I wrote some system of generators, but I will not work with that one. So I will work with a different system of generators. So I only take these W tildes for W in the finite while group, and I also take the lattice. So if I am in the type A situation, then points are, so it's braids in a complement to a pole, and then if, or maybe better said, if I'm working with, maybe I'll just without drawing, I'll say, so I'm working with fundamental group of configurations, configuration space of C star, then the lattice corresponds to each point running on its own orbit without orbits non-intersecting. Okay, so yeah, so there is a that system of generators, and a particularly nice answer. I mean, there are these two versions with G tilde and with N tilde. Let me state the one with G tilde. Then these things corresponding to finite Weyl group elements, they just go to the structure sheaf of the closure of the graph. So remember, like this. So we have this Grothendieck-Springer map. And if you restrict it to the regular locus, then it's gonna be a ramified covering. So we have an action of W, and for every element of W, you can take the graph of that action, close, and take the closure, and take the structure sheaf of that closure. And for a lattice element, I can just take the line bundle on the diagonal. But by the way, so a proof of this theorem is not, just forget about constructible side. So you can ask, how do I check that there exists an action? Clearly, this formula is characterized actually uniquely. How do I check the relations? And that's actually can be done without invoking the constructible side, but I don't know a direct proof. So we have a paper with Simon where we prove it, but so a paper with Risch, and particularly, so it uses localization, like positive characteristic localization. So it looks like an elementary calculation with kernels, but it's actually, I think it's a tricky one. So I don't know if there is a direct proof. I am certainly very, very interested if there is one. Okay, but so now everything really rests on the following point. So I'm going to, talk about this noncommutative Springer resolution, but as I said, we motivation largely comes to connection to representation theory, and what makes this connection work, what really connects it to representation theory, is that the same affine action arises in another context. In particular, something that is not a focus on this talk, but I still want to mention it, that derived category of coherences on G tilde or N tilde, both of them are related to modular representations, and then when you talk about modular representations, we take principal block, and when we take principal block, we have this now wall crossing functors acting, and so that's the formalism which yields, in particular, an action of the affine Bragg group on the derived category, and that action turns out to coincide with this action. But okay, so to flesh it out a little bit, so here is a formal theorem that exists a unique T structure on these two categories. So there's a normalization axiom and there's break positivity axiom, and then that's it. So normalization is that our gamma is T exact, and that the generators, but now here I have to go back to the Coxeter generators, and that's essential. So alpha runs over the virtues of affine Hecke graph. So they act by, say, right exact functors. And then this T structure has various nice properties. In particular, its projective generator is of the heart is a vector bundle. I mean, that's what's called tilting vector bundle in algebraic geometry. So basically, it's some rather concrete data. So we have a vector bundle. We can form a centromorphin ring, and then we have this natural functor, and it turns out to be equivalent. And so there in people. So maybe I think Van den Berg defined this concept of Bond and Orlov. I should say it's non-commutative resolution of N in the terminology of Van den Berg. and bundle Orlov. So for every single space, one can there is something just called a non-commutative resolution, and that's an example in our situation. Yeah, so I just wrote these two versions for Springer and Grothendieck Springer. And just to make this a little bit more concrete, so in SL2 case, it's very easy to write it explicitly. E is just O plus O1. So I should say E itself is not really well defined. It's in decomposable sum and R. So the algebra A is well defined up to Merit equivalence. So yes, and then the A is this subring in the ring of matrices where diagonal entries are even and off-diagonal odd. Okay, so how does this help us? So now to give, finally, I am ready to give the answer to my question. So basically, the locally over a given orbit, so if I'm interested in the image of the T structure from the constructible side, locally over a given orbit, it comes from this non-commutative Springer, and then to glue it all together for different orbits, we need this perverse coherent shift. So here is a formal theorem that, okay, so we have this equivalence. And yeah, so once we have, non-equivariant versions, so A can be made equivariant, E can be made equivariant, G check acts on A, so we have equivalence with equivariant modules. And voila, so here's the answer. So inside the constructible derived category, we have the abelian heart. Here it is. And on the right-hand side in the coherent world, it corresponds to perverse coherent equivariant A modules of middle perversity. One way to say it is that the objects in DB of A mod, so that if you forget the A, so there's a forgetful function to coherent shift, but if you apply this forgetful function, you get into perverse coherent of middle perversity. So, okay, and now just, I'm wrapping up, but just to list the applications. So why is this, why you should care about this non-commutative Springer? Because if you, here is, if you're a representation theorist, so here are some reasons. So now I fix an important, and let's just reduce it, modular corresponding maximum ideal in the center. So AE is a corresponding central reduction. So the first motivating kind of connection to representation theory is that if I happen to be in positive characteristic and Fox-Tor number, then this category of AE, well, or AE modules, obviously, sorry. AE modules is the same as category of G modules with a fixed central character determined by E. Then there is another connection that's...
And you need like a principal block, right? On the right-hand side.
Right, it's part of this central character. I mean,
okay.
Yeah, because of the lack of time, I'm not saying how it's, what the central character is, but yes, the answer is that P character is E and Harishchandra character is anything regular interval. And then there's also connection to representations of affine layers with the critical level. And so it is a short paper in my former graduate student who left this area of math, but Chen Lin, but related to his thesis. So it's, but yeah, it's a short paper based on a few long papers by Dennis and Ed. So here we are say over C, and then we can identify it with the sort of highest weight modules at the critical level with a fixed central character, where again there's some order where the connection has residue. And then there is the following. It's a conjecture. It's stated a conjecture in our paper with Ivan, and there is some related work back in Kremnitzer and Tanisaki. So it's conjecture with a clear approach to its proof. So maybe. Yeah, so that should be equivalent to models of a quantum group, because the continuing quantum group at the root of unity, also with a fixed central character. With a fixed central character. So this has a, and in terms of concrete applications, well, A was this motivating application, so proof of Lustig's conjectures from his, I guess, 1999 paper, Basis in Equivariant K Theory 2, which described described canonical basis in homology of a Springer fiber and relates to characters of irreducible modules over G over Lie algebra in characteristic P. Yeah. So how should I say? It's a proof for definite large P. The conjecture is not for definite large P. So for indefinitely large P. So yeah, I certainly will not be recording the conjecture, but just just say that answer is in terms of canonical basis, in terms of the canonical basis in, well, Grothendieck group, or you can say homology of Springer fiber. And there are potential applications on character formulas for affine Lie algebra modules and quantum group modules. So yeah, we can discuss if people are interested what is needed to complete this. So this, I think, still has not been done, and it's well worth doing. Okay, and so now just a concluding remark. So, you know, one of the ways to think about it, like context where this fits, is that this AE module, it's yeah, maybe I should just to never said this, that the Grothendieck group of AE modules is just the Grothendieck group of this corresponding Springer fiber. Well, by Cherenkov, it's also homology of the Springer fiber. So this is also by the work of Lustig and Ginzburg. This is the standard representation, sometimes reducible, of H affine. So in other words, Eva Hor invariant vectors in a standard representation of the Beatty group. And so, okay, so we've went through all the story, and which can be thought of as, you know, various aspects of the study of the category, which is, you know, category finds this part of representation of the Beatty group, and local geometric Langlands really talks about the bigger categories, which are category 5 representations of the full Peetie group, and there is a proposal by Franklin and Gatsgary, which is actually generalizes this theorem B above. But so yeah, so I think that's a really interesting direction to study. And another generalization that I will have not touched upon here is replacing important column by other subjective singularities, but I will maybe mention this in my workshop talk. Okay, so that's it. Stop here. So I see there are some questions in the chat. Yeah, so I think the answer is to George's question about composition theorem. I think the answer is really no, but to be fair, Pramod has some result that he calls an analog of the composition theorem. My understanding is that it's kind of, maybe it works sometimes, but in a limited generality, so maybe it's an interesting result, but I think in many cases that we care about, this doesn't apply. And well, okay, so as I said, like Perovskite coherent shifts, so there's Perovskite coherent extension if the boundary has basically codimension more than one. Well, so more precisely, so there is a there is Perovskite coherent shifts in this under these assumptions. This is perversity function, which is monotone and comonotone, but then if there is a point so that for every point in the closure you have strict, the two inequalities are strict, then you can define a unique extension. But well, that's maybe a kind of cheap formal answer, but there may be more kind of, there may be some special kind of classes of shifts which it works, but like say like in the Schnell's paper, complex settings, so that I can't give a formal statement.
I have a question about A. What is in the sort of constructible side? Can you tell me what A is? Like, I was a little bit surprised you were doing a generator of a category, but it only had two objects for SL2. What's it a generator of? So
sorry. So question about A. So where A is what? A in where? In the theorem?
Or maybe what E is, the projective generator that A is the endomorphism ring of.
Right.
Okay. Type A1 delta.
Yes, I can say a few things about that. So ways to think about E. So this is a vector bundle, say on N tilde or G tilde. So one thing to say here is that if you restrict it to the zero section, then it's essentially, and you work in characteristic, say P more than H, then this is essentially direct image of, or some other line bundle under Frobenius. I mean, up to, it's or E, maybe up to dualizing in the way in a proper normalization. I think in the normalization I worked in, it will be dual thing. So I reminded the direct image of OP1 under Frobenius is O plus O minus 1 to the power P minus 1. So that's when I say is isomorphic, I mean that E is really well defined up to equi-constitutedness. So I only care about decomposable summands, but not about the multiplicities. I mean, but that thing is not, I mean, it's okay to can compute it for projective space. Yeah, you can say that, you know, it works. So the story works for G mod P. And then for Pn, it's really easy. For Pn, we get essentially O plus O.
And in the constructible side, I should just be thinking of a bunch of Rukier complexes?
No, so no, I wouldn't say so.
Well, I mean, these are all standard objects that you're writing down, or I guess up there you had a co-standard object.
Well, because, you know, that was my next sentence, that in those specific cases, yes, it's easy to say what they are, but in already for SL3, I mean, yeah, with Simon, we computed it explicitly. And it's there's one feature is that it's not a pulled back in these easy cases, it's pulled back from the base. Already for SL3, it's not pulled back from the base. So for SL3, until like SL3, so E has, if I remember correctly, 3 summands of rank 1 and 3 summands of rank 1 and 3 summands of rank 2. And of those summands of rank 2, so one of this, one in the second list, one of these is not pulled back from, is not pulled back. It's an extension of 2 things. Pulled back from. But so if you, there is a sort of concrete way to write it down, but in that way, I don't know how to directly check the properties. So if you like, okay, so we can introduce the functors psi alpha, where, so basically the geometric wall crossing functors. Where for, so alpha has to be a vertex of the affine Denkin graph. But if alpha is actually a vertex of finite Denkin graph, so if, then it's easy to say what it is. Then psi alpha is just so yeah, so these are endofunctors of GB Koch G tilde. And so psi alpha is just pi alpha star pi alpha lower star, where pi alpha is a map from G tilde to G tilde alpha. And then you can say that E can be chosen to be like a sum of some so you consider certain sequences of these functors and apply it to O, and then you get that. So if and you know, I can say what xi alpha 0 is. I'll just take like 3 minutes, but if
can you address my fundamental confusion though, which is why there's finitely many things here, whereas the anti-spherical module has infinitely many decomposable objects. Like, this is supposed to be a projective generator of something.
It is a projective generator, but not of the affine. Not of the category that you're used to.
What is it, a projective generator?
Can I try?
Yes.
So equivalence is with G equivalent category.
Yes. No, it's also right. Yes. So that's one.
Like, morally, the way how I understand it, which may not be perfect, but you take this in decomposable summands, and then you need to multiply them with representations of G.
Right. But even then, it will be a projective generator in this module category, and the constructible side is identified with this perverse coherent module category. So there is another aspect. But yes, in first approximation. Yes. So no, that's right. So actually, as you see from this description, so yeah, okay, it's related to tilting generator. I think it's the yeah. If you take tiltings on the constructible side and restrict equivariance, then you get E.
But I'm still confused because there still seem like there's infinitely many tiltings.
There are many tiltings, but when you restrict equivariance, so for example, so if you take as I think was mentioned before, like if you so now on constructible side, so if you just take this perverse sheaves like I0 flex, so it contains tilting like psi W0 and TW0. So the big projective on the fine dimensional flex, and then if you convolve it with the Gates-Geary central sheaf, and this is a tilting.
Okay.
You get so all things. So TW for W maximal in W in the two-sided coset is a summand in such a thing.
Right.
But all these things, when you pull the coherent side and restrict equivariance, they become the operation of tensoring with 0V become just tensoring with a vector bundle. So it's not adding anything. So basically, all this infinite collection of tiltings, it's enough for me to remember only one of them. So I don't know if that addresses your question. But yes, so I think it's a good question of what's the exact relation between E and tiltings on the dual side, and maybe I'll answer this later.
Oh, thank you.
No, I think it is true that yes, that E can be obtained as a, just taking the image of tilting from the constructible side and forgetting invariance.
So maybe we already want to finish, but let me try to ask this. So in the very beginning, Roma, you mentioned this result about self-filtrations, and you mentioned that you may want to say something about the proof after the end of the talk.
Yeah, sure. So I mean, there's actually there's a proof, and then there's a stronger, there's a corollary. So maybe let me start with the corollary. Recall the asymptotic Hecke algebra J. Yeah, probably I will not.
So you want to say do not recall?
No, I want to say that you should recall if you can, but if you can't, that I'm not going to help. And so J is by construction, it's a sum over two-sided cells of JC. And so now I'm we'll say how this JC is related to our story. And so corollary is that something like this holds, that JC is the K group as a base string, it's isomorphic to K group of bimodules which are equivariant with respect to the centralizer of E and semisimple.
And of course, you want to sum over all orbits. Ah, no, I mean, you have a C. Okay.
Yeah, E, right. So for JC, E is so the reason is that well, I mean, how this definition that I didn't recall works. I mean, you have to take things and then you have to multiply them. I mean, convolve them and then truncate at some degree, which corresponds to the A function. But the point is, and also discard smaller cells. But the point is that, well, first, discarding smaller cells means throwing away orbits in the closure and truncating. So because of this shift, I mean, this perverse coherent business, so it basically it says that when we construct this equivalence, so over the orbit, we just get bimodules, but the equivalence incorporates a shift by a function. So a function is exactly codimension of the orbit. And then this truncation at degree A becomes just truncation degree 0. So you just get usual product. Right. So about the proof, I mean, actually the most subtle point is comparing the bijections. So in a way, the fact that you have ideals, the fact that you have based ideals, and this is like finest partition, which leads to those based ideals, that's, you know, should imagine. I think it's not hard to imagine, it basically follows from this picture. So yeah, so the subtle thing is to compare the bijections, and this was actually mentioned, I think, in a previous talk, maybe it's Xian's talk, that Lustig defines, yeah, so well, I should say it's the that we get based ideals, and so cells. But yes, so comparing bijections between the set of C and check. So Lustig's definition proceeds something along the following lines. So he uses the homomorphism from H affine to J of, well, Q or V inverse. So the point is, J is an algebra over Z. And then we can extend, well, let's extend scalars to C. So let's say it's an algebra over C. And H has this variable V. And now what he says is the following. So, okay, so let's just take some representation of JC and then pull it, but define over a small field over C. And then we extend scalars and then we pull back. Then we get some representations of H affine. So let's look at its just central character. So then we get some element in the dual group, but the dual group, so pull, yeah, start, dual group over this power series. So start with a representation of JC over C, and then pull back, and then consider, so take central character. So we get some elements, maybe Z in G check of, C of VB. So Lustig says that it has, so this Z is equal to the following. So, so there is some Z sort of constant defined over C times the canonical element attached to the nilpotent to this auto triple times gamma of V, where gamma is sort of, I should say it's gamma of diagonal matrix. The inverse, where gamma is a homomorphism from SL2 to G, check, corresponding, well, such as the SL2 triple contains E. But now, with all this, we can connect all this to the construction of our equivalence, and basically we use that the monodromic filtration coincides with weight filtration, and weight filtration has to do with powers of V. So that's
okay. Thanks.
our construction via Garber's theorem. Yes, wait. Okay. Any other questions?
So it's getting a little bit late. I wonder if it makes sense to maybe thank the speaker at this point, and then Thank you, Roman, for the talk.